Hello, my name is George Athanasakis, and I want to welcome you to the RivMorph webcast. In this webcast, we're going to go through basic geomorphic data collection using the RivMorph software. RivMorph is a fluviogeomorphology software package, and we like to think that it has everything that you need to do processing of stream restoration data plus do a natural channel design right at your fingertips. And for more information about RivMorph, please visit our website at www.rivermorph.com or email us at info@rivermorph.com. So today I'm going to go over just the basic layout of the software and how to process geomorphic data. And I'm going to go into cross sections a little bit more in detail and then a little bit less detail on the other items such as profile and particles, because a lot of the stuff that you do is similar between cross sections, profiles, and particles. So the way the software is basically organized is, first of all, you're going to open up a database, and you can either create a new database and open up an existing database. If you have existing data and you want to combine the data into another database, for instance, if you're collecting reference reach data and then you want to pull that data into a master database, you can use import and export. So it's pretty easy to get data in and out of RivMorph and to combine data sets. So once you get a database set up, the way that that database is organized is, on the highest scale, it's river, and then rivers can have multiple reaches, and then reaches can have multiple geomorphic data sets, so cross sections, profiles, particles, etc. And then once you create a geomorphic data set, for instance a riffle, it's pretty much displayed over to the right. And then with RivMorph, you have a number of pop-up tools, like for instance regime equations, where you can then be working in the software and then open up regime equations and make some quick calculations. And there's other webcasts that deal with the various tools that are within RivMorph. Okay, so if we're going to do add a geomorphic data set, the first thing we're going to do is do right-click, add cross-sections, and then I'll name the cross-section I want to name it, or call it whatever I want to name it, hit OK. In this case, I'm just going to cancel out. And then this data screen will appear. So I can put in my basic survey information, my distance across the cross section, my rod readings, my basic benchmark information. I can compute elevations, and then I can identify special features about that cross section. And one, very special feature obviously is bankful. So I can either type in BKF, or I can do a right click and then select BKF, for instance. And then as far as processing the data, I can cut, copy, and paste, very similar to Excel, insert rows, delete rows, and I can also sort the data. And then it's very important that I identify what the facet type is within RivMorph. So it can be riffle, pool, run, glide, step. By default, it's going to be a riffle, but I can name it whatever I want to name it, or call that facet type whatever I want to call it. I can also import HEC-RAS geometry files, or I can export out RivMorph files into creating a HEC-RAS file. So if I want to compute water surface profiles, I can do that external to RivMorph by using HEC-RAS. So once I get my data in, I can then basically look at the graph, and so you can see the general shape of the cross section, and then there's a line through bankful, and you can see the bankful parameters across the top. You can also see the inner berm properties as well. And RivMorph is meant to be very graphical. So let's say I get back in the office and I see this feature at this lower elevation, so I can just drag my mouse down and see how that would change the calculations. And then if I want to go back to the original bankful call, I'll just hit reset bankful and it'll go back to that value. And so anyway, that's how I would process bankful information and particularly change it. Now, one thing I'll point out is, let's say that I want to go with that lower feature. I can tell where I'm at coordinate-wise by looking at the lower left-hand corner. Anytime I hover my mouse, it's going to give me those coordinates. In this case, around 19.6, then I would have to go to my data and then move that bankful call down to 16.9 was actually the value there. Or I'm sorry, 19.6 is correct. Yeah, so I could then move that bankful down to 19.6 if I wanted to do that. Okay, so on this graph, I can zoom in, zoom out. I can show the width of the flood-prone area if I wanted to do that, which is illustrated now by that dashed line. I can, if I don't want to show the inner berm, I can remove the inner berm by simply unchecking that. And inner berm is a low flow depositional feature that tends to form in channels. So again, if I want to show that inner berm, I can show it back, and I can move bankful up and down, or if I want to move my inner berm up and down, I can just set the mouse function onto inner berm, which allows me to move it up and down as well. And then again, if I want to just reset these back to the original values that I had, I can just hit reset bankful and it can go back to that. Okay. Now, we've got a number of tools that we've customized. So one tool is limits. So what limits does is it allows you to remove an ineffective flow area or a disconnected side channel. So as this graph kind of illustrates, this particular cross section has 6 different side channels. If any of these side channels, wherever the side channels fall below the bankful line, that information is going to automatically be included into the bankful calculation. But if you have an ineffective flow area, you can remove that. So, and what an ineffective flow area is basically if you start walking in the side channel below the bankful elevation, you walk all the way through that side channel and you come back into the main channel below bankful, then that channel is hydraulically connected because you never went above bankful. But if you do that and you walk above bankful, then it's disconnected and you don't want to include it in your bankful calculations. So the way that you can remove it is by simply putting in the x1 and the x2 coordinates, of course hovering your mouse to get what those coordinates are. And in this case, I don't have disconnected side channels, so I'm just going to cancel that. Okay. Another thing you can do with RibMorph is cells. You can break the cross-section up into 5 user-defined cells. The reason why you may want to do this is because when it comes to sediment transport in a braided channel, most of the sediment transport occurs in the deepest channel because that's where the stream power is the highest. So you may want to isolate that particular cell and do hydraulic calculations on that particular cell as opposed to averaging the entire cross-section. And basically the cells tool within RibMorph would allow you to do that. In this case, again, I'm just going to cancel that out. Depression is another way to remove an ineffective flow area, but it only allows you to remove that ineffective flow area on one side. So I personally like to use limits whenever I have to do that. What overlay does is it allows me to overlay multiple cross-sections. So if I'm monitoring a cross-section from year to year, I can, when I hit this button, it'll pull up all the cross-sections in my database. I can select them when I want to use and hit OK. And this particular data set is not set up for monitoring, but if it was, I could hit OK, and then it would overlay those 2 cross-sections on top of each other. And if I hit delta, that would get the difference in the cross-sectional area. So I can see how much that cross-section has changed from one year to the other. This drawing tool allows me with mouse clicks to create a cross-section, which I can then export into another cross-section and create a separate cross-section for. Okay, so that's basically the graph component. Now, one thing I'll just point out is if you want to manipulate the graph at all, any place that you see a graph, there's an icon that has a little graph symbol and it usually says options next to it. So what you do then is once you pull up options, you can then change the graph titles, you can alter the axis, you can have a user-defined X and Y scale, or if you want RibMorph to go in and figure out what's the best scale, you can just use variable origin. I can change my font size, I can change my background, have like a drop shadow, raised letters, and I can also create import and export. So if I want to create an image of this that I can drop into a report, drop into PowerPoint, I would just hit System and then hit Browse, and then I would name it what I want to call it, hit Save, and then that would create that export image. Okay, so summary, up to this point we've been looking at the basic width and depth and area. So now summary gets me more detailed information like width to depth ratio, wetted perimeter, hydraulic radius, to use more for hydraulic calculations. And one thing I'll point out too is the width of the flood prone area. If I run out of data, which in this case this dashed line never intersects the data that I have, so RibMorph is automatically going to just assume vertical when we run out of data. But if you knew that if the floodplain went really wide here, like I'm kind of tracing out with my mouse, and it went much wider than the data, then I can hit this check WFPA override, and I can type in the width of the flood prone area. And then once I get all this data in, I can start to do a broad level stream classification. Trenchment ratio is 9.85. indicating slightly entrenched. Width to upper ratio around 19.33. So at this point I don't have slope, I don't have particle, but I can tell that I'm headed towards a C classification. This next tool, hydraulics by stages, what this does is it allows me to look at the hydraulic properties at all different stages rather than just concentrating in on bankfull or inner berm. So if I create a graph here, I can look at area versus depth. And I'll do area on the x-axis, depth on the y-axis. And this is a hydraulic geometry plot of how area varies with depth. Okay? And if I want to get more detailed information like shear stress, discharge, I have to give Rivermorph a little bit more information. So I have to give it a velocity formula, which in this case I'll choose Manning's equation. And then I have to give it a determine how I'm going to figure out Manning's n, which in this case I'll say Limerinos, which requires me to put in a D84. And then I can select a sediment transport relationship. In this case, I'll say Meyer-Peter-Mueller, which requires some input parameters. And then I can either define a constant slope for all stages, or I can change and vary slope with stage. And remember, we always do our hydraulics at a riffle. So I can define a low slope at low flow, which tends to be steeper. And then as we approach bankfull, the slope tends to flatten out. So I can define how that slope varies with stage, but in this case I'll just use a constant slope, hit next, hit finished, and then you'll see I'll have more detailed information now about this particular cross section, and now I can graph quite a few more parameters. So for instance, if I wanted to look at how shear stress, or in this case I'm going to say power, how power varies with depth, I now have a geometry plot of power versus depth. So this allows me to do more in-depth analysis of that particular cross-section. And then with Rivermorph, we want to make it to where, again, everything about your design can be right at your fingertips. So if this is a riffle, you can save a picture of what that looks like. And you can keep that with the database, so you have a record of what that particular cross-section looked like. All right, so that's cross-sections in a nutshell. So if I go over here to profile, and again, the way I would create a profile, I do a right-click, add profile, and then name it, but I've already got a profile set up, so I'm just going to go with that one. So like cross-section, I'll put in my basic survey information. Distance is distance along the tape. CH is the thou egg shot, water surface, bankfull, and up to 4 additional user-defined features like low bank or high bank. And then if I know what the facet is, I can identify that facet like riffle, run, pool, or glide, or I could type in R for riffle, U for run, P for pool, G for glide. And as long as Rivermorph sees under notes, the R space or riffle is the first thing it sees, it can then bring over those facets. So for instance, if you wanted your note to read top of riffle, the way you ought to enter it into Rivermorph would be riffle space top. And then Rivermorph can then read that and show that. So then turning points is where if you have a turning point for your profile, you'd put it in here. The key here is that you have to give it a station at which point that turning point kicks in. So this is indicating that beginning around station 1 plus 45, that's when this new turning point kicks in and that new height of instrument kicks in. So then ultimately what we want to do is get a bunch of measurements out of here, like riffle slope, max depth of the riffle, max depth of the pool, because we want to use this to develop dimensionless ratios to help with the design. So first thing I want to do is create the graph, which is shown here. In this case, I have a best fit line through bankfull, but if for any reason that best fit line was not there, the way you would create it is you go to trends under graph options, and you go to your third data set. The first data set is the bow egg, second data set is water surface, third data set is bankfull, and it's the same way it appears in the legend here. Hit best fit, hit apply, and that would put that best fit line through bankfull. And if you want to see your facets, you can hit tags, and that'll show where your riffle, run, pull, and glide is. If you want to show your cross sections, you can tap these boxes here, and you can show where those individual cross sections fall out. And one thing I'll point out too, well, basically what we want to do now is go through and make a series of measurements. And if you open up this measurement guide, excuse me, let me pull that back up. So if I make this graph a little bit bigger, open up this measurement guide, this pretty much shows you where you need to take all these measurements. And this is based on Roskin's data, where he indicates that you should take your max glide depth, max pool depth, etc., and where you take your water surface shots for your riffle, pool, run, and glide. Okay, so that shows you where we need to make the measurements. So the way you make the measurements in Geomorphic, again, it's very graphical. So I'm just going to take my mouse, drag it up to bankful. So I'm tracing now max pool depths. Okay, so I made a series of 4 measurements. I'm going to minimize this now. And all that data was captured here. I'm going to go over to max pool depth. And I'm going to do a right click and then paste those values in. I made those measurements very quickly, so I'm just going to leave the original data in here. Again, just kind of illustrating how you go about making those measurements. So once I make the measurements, I can clear the list out. And then I can go back and make another series of measurements. So I may want to measure like pool lengths and pool slopes. So again, I would simply trace those measurements out, and that data is being captured as I do that. And if I want to measure pool lengths and slopes at the same time, as long as I start at the beginning of the pool and end at the end of the pool, I'm capturing both slope and length at the same time. So again, I would capture that data, paste it. In this case, I'm going to reset list. So that's a couple ways to show how you end up getting measurements here. Now, another way, if you're not comfortable with drawing it out and you really want the actual data, you go into select mode. And what this does is it allows you to then go in and select the actual point on the water surface. So that'd be the first point, second point, and then I'd hit add and then clear, and that would add that data to this list over here. So then I could go and then make another series of measurements along here. So I could then go to my next pool and basically do the same thing, add and then clear, and now I've got 2 sets of measurements in there. And then again, I would copy, I do a right click to then add that value in. Okay, so that's how you make your profile measurements on here. So I'm going to go to particles now. So same situation, I'm going to do a right click, and I have options. I can create a pebble count, a sieve analysis, or if I have multiple pebble counts, I can combine them into a single pebble count. So for instance, if I have a riffle pebble count and a pool pebble count, I want to make a combined reach average pebble count, I could do that. In this case, I'm going to cancel it out because I've already got that data. So it's simply, the way this works, this would be for a woman pebble count. I'm just going to type in the number of occurrences for the different sizes here. And then from that, I can get a D84, a D50%, silt, clay, sand, gravel, cobble, boulder, bedrock. If I want to, it's really important that I identify the sample type. If it's a riffle, I want to designate that way. If it's a reach average, because I use reach average for classification, I use riffle for sediment transport analysis. I can then look at a linear graph. I can also look at a bar graph. And if I want to do overlays, I could overlay multiple pebble counts onto a single graph. So that's what that would look like. And then if I want to create a bar sample, and typically for bar samples we do sieve analysis. So in this case, do a right click, add a particle distribution. I would do a sieve analysis as indicated here. I'll cancel that out though. First time I would load this up, all these fields would be blank, so I'd use the sieve analysis. I would just select the sieves I want to use, hit apply, and then close, and then I can type these values in. Again, it's important that I identify the sample type. It'll be a bar sample in this case typically if I'm doing a sieve analysis. Then I can see a linear graph as well as a bar graph on that. So that's basically how the particle data would tend to work. Okay, so now if I go to classification, and if I go to the screen for the first time, all these fields are going to be blank. And all my riffles are going to appear in this drop-down box because I always base my classifications on a riffle. All my pebble counts would appear here. All of my velocity calculations would appear here. And then my profiles would appear as well. And then, again, now we can take advantage of the database. So if I want to hit the riffle button, it's going to go yellow to show what's being loaded. And it's going to load up all the riffle information. Hit the profile, it's going to load up the water surface. I hit D50, it's going to load up that D50 for that reach average pebble count. If I hit VQ, it's going to load up my velocity discharge calculations that I made. And then from that, I can create an output of this by hitting this worksheet form. In the interest of time, I'm not going to do that. And then anytime you see a calculator, it basically means there's another way to calculate. So for instance, if I know sinuosity and water surface slope, I can back calculate valley slope. And if I want to use that, I hit yes, and it'll automatically calculate that for me. So anytime you see a calculator, it means there's a way to back calculate that value. This is a reference reach. This is where I'm going to designate it at the bottom. That's how I'm going to let RiverMorph know that's a reference reach. It has bedrock control. I can identify that as well. Or if it's like an E4 headed to a C4, I can designate that as well. Okay. And then if there's any extra information about that cross section or about the reach, I can put that in there as well. Okay, so we've got the classification done, so now we need to fill out ratios. So what ratios is used for is if we're doing a natural channel design and we want to use a reference reach, then we use dimensionless ratios about a reference reach in order to set up and do an initial cut of the design of a impaired reach that we're trying to restore. And so we use the dimensionless ratios to do that first cut of the design, then we check for sediment transport using both competency and capacity. And if for some reason that doesn't work out, if the competency and capacity don't check out, then we have to vary slope or vary parameters, vary the sinuosity, vary the race curvature, vary the meander wavelength, using the range of values that we have from the reference reach, and then recalculate sediment transport and basically go back and iterate until we have a design that works. So as far as generating the dimensionless ratios, when you first come to this screen, it's going to all be blank, which I'm kind of unloading now. So all you have to do is check the values that you want to use. If you have multiple riffles, you could check multiple riffles if you wanted to do that. That's going to load the data up, and then if I want to see the dimensionless ratios, I can hit Views Dimensionless Ratio. Pattern is going to be the meander wavelength, race curvature, belt width. I can type these values in if I'm using RiverMorph GIS, which we talk about in a future webcast that goes over the RiverMorph tools. Then I can download that data directly by using RiverMorph GIS. And then on profile, you'll notice this looks very similar to the measurement tab. And so you just select the profile that you want to use at the bottom. And again, if I want to see the dimensionless ratios, I can do that as well. And then if I'm, information like point bar slope, the velocity discharge calculation method, and low bank height information for low bank height ratio would go under this extra information. And then from that, I can generate Roskin's worksheet, dimensionless ratios worksheet, that automatically populate that worksheet and allow you to view all those dimensionless ratios. Okay, so that's basically how you would process basic geomorphic data within RiverMorph. And I'd like to thank you for sitting in on this webcast. If you have any questions at all about RiverMorph, please feel free to contact us at either info@rivermorph.com or by visiting our website at www.rivermorph.com. And again, RiverMorph is a fluvial geomorphology based software package that has all the tools that you need to do river restoration and river analysis right at your fingertips. Thank you.